If you went looking for spicy math, you're in the right place. Today we're going to look at the Laplace transform, particularly how it applies to piecewise or discontinuous functions. If we recall, the Laplace transform takes some function f of t. We like to symbolize it with this curly L and curly brackets. We define that as the integral from 0 to infinity of e to the negative st, where s is this new variable we're going to transform our function into, times the function itself, dt. So we can also write this as some big F, usually with s. So the properties of this transform are such that we really like it for differential equations because it lets us turn a nasty calculus looking thing, and it lets us instead solve the differential equations with algebra. That's the alleged benefit of doing these. If you've actually worked a couple of these and you've worked through all the partial fractions that entail when you do them, I'm not really convinced the algebra is less work than doing something like an integrating factor or variation of parameters. But when we're actually looking at piecewise functions, I think is really where the Laplace transform shines. So the idea is we're looking at a function that changes. We might have some differential equation. I'm just going to write a really generic one equal to some function g on the right-hand side. And the twist is that g, what g is doing is time dependent. So it may be some function, maybe t squared from 0 to 2 seconds. But then it's just 0 after that. If we were to actually solve this equation, we would need to kind of work it out twice. We solve it once for this, we solve it for that, and then maybe we use the condition at 2 seconds to connect the two solutions and build the overall picture here. When we have the Laplace transform, we're evaluating this interval from 0 to infinity. So if we are working in that range, or domain, I guess, as it were, we can carefully define our function g in a new way to kind of take everything out in one fell swoop. So the way we do that is really based off something called the unit step function, or sometimes called the Heaviside step function. We define it as u of t is equal to, it's just 0 when t is less than 0, and it's equal to 1 when t is greater than 0. So the result is, if that's t equals 0, the function is just 0 everywhere to the left of that. We get to 0, and all of a sudden it steps up suddenly, and we have 1. It's a step. So it's 0 over here, it's a value 1 over here. And so the idea is that the function is kind of off for t less than 0, and the function is on after that. So we can take our unit step function and multiply it by some other function that we're interested in, t, for example, and it would be nothing before that, and then it would be a linear function where the step function is equal to 1. So you can kind of like sift out regions of space where you want the function to behave a certain way. We can shift where that step is going to be by simply subtracting a from our value of t. And so now this is going to be equal to 0 when t minus a is less than 0. And it's going to be equal to 1 when 0 is less than t minus a. And so now what this is going to do is, if this was originally 0 and this is my value a, I've shifted my step to be there. So if I want to start my function doing something at t equals 5 seconds, I'm going to set a equal to 5, and now it's going to be off anytime before that, and it suddenly turns on after that. Okay, we've made some steps. Big deal. Well, now, not only can we shift this step, but we can also kind of create little windows where the function is on, and then it turns off after some time later. So it's going to be 0, it's going to step up, and then it's going to go down. And when we combine steps and windows like this, we can kind of build any sort of functions that we want throughout the domain. So here's the definition of a window function. We're going to notate it as a capital pi. So the big guy you might see in infinite product, or just the little 3.14 dot 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 got a little bigger. We subscript it with a and b, and it's a function of t. And really what this is it is a shifted step function that shifts to a. We're going to subtract from that another shifted step function based on b. So this is how we would write a window function as a difference of step functions. And then we can also think of this piecewise as it's 0 and 0 and then 1. So it's 0 for t less than a. It's going to be also 0 for t greater than b. And then finally, it's going to be 1 in between those bounds a and b. So a is less than t is less than b. So by creating a combination of step functions, I can now make a window function such that it's 0 less than a, 0 greater than b, and it's the unit step equal to 1 everywhere in between. So if I multiply my window function by, 2t squared, I can make it behave like that quadratic just within these bounds and have it turn off or be something different somewhere else. So by combining, adding together window functions over different shifts, we can build any piecewise function we want and then can integrate it in our Laplace transform in one fell swoop. So let's get a little example of how we might actually do this. Our goal is going to be to write the following function, f of t. We'll have it be equal to 3 for a little bit, 1 for a little bit, t for a little bit, and then let's go a little wild and have it be t squared over 10 for a little bit. So we're going to define t is less than 2 for 3. Between 2 and 5, it'll be equal to 1. Between 5 and 8, it'll be equal to t. And then when t is greater than 8, it'll be t squared over 10. So this is a very strange looking function. But if we draw this on the interval over which the Laplace transform is defined, we have 0 down there. And we're going to start at 3. And it's just a line. And then it drops down to 1 between 2 and 5. And it's a line there. And then at t equals 5, it becomes a linear function again. So at t equals 5, this is equal to 5, so it jumps kind of way up there. And it's a linear function until about 8. And then it is a quadratic function after that. So we get 8 squared, 64 over 10, about 6.4. We're kind of a little bit bigger from where we left off, and then it's going to swoop up like a quadratic function from there on out. So we have this four-way piecewise function, and now by writing it out, as we're about to do, in terms of the step and window functions, we can have something we can ultimately integrate in one step. So here's what we do. We're going to basically just multiply each of these things by the appropriate window function. So we're going to say that f of t is equal to 3 times the window of 0 to 2. Then we're going to add to that 1 times the window from 2 to 5. Next, we're going to have t multiplied by the window from 5 to 8. And then finally, this last one here is only defined greater than 8. It doesn't have an end to its window. And so that's just going to be the step function from 8 onwards. So we're going to multiply t squared over 10 by u of t minus 8. And that is our full function here. Once you have the windows, you can probably really kind of use the identity up here to rewrite it in terms of the u's. That's typically going to be the best way to integrate it. As we're going to see, we're about to define what the Laplace transform of u looks like. So let's start doing that. Next page. We want to find the Laplace transform of u of t minus a. We're going to do the shift in general just to kind of get it over with. This is going to be defined as, because it's 0 everywhere before a, that part of the Laplace transform is just 0. So our bounds are going to shift to be from a to infinity. We're going to integrate e to the negative st times 1. That's what the function u is when it's greater than a. And so this is a pretty simple integral to do. We bring down a factor of negative 1 over s times the exponential. And we evaluate that from a to infinity. Well, when a negative exponential is infinity, that just goes to 0. So we get 0 minus minus. The minus sign's already there, so we pick up a plus. We evaluate the exponential t at a, and so we get 1 over s e to the negative sa. So if we just have a step function, the Laplace transform we get out of that is 1 over s times e to the minus sa. So that is a useful identity when we have discontinuous functions. Likewise, we can also define the Laplace transform for the window function. And that's just basically going to be a difference of two different step functions. So we employ the linearity of the Laplace transform operator, and we're just going to act it once on the A1, and we're going to act it again on the B1, and we're just going to basically subtract these two results, one evaluated at A, the other evaluated at B. And the result is 1 over s times e to the negative sa minus e to the negative sb. So that's our window. The whole idea of the window function and step function is to allow a single function to take different values or different, to become different functions over different t values. And so we really don't care about the step function by itself or the window function by itself, but some function multiplied by either of those. So we're going to look at f of t minus a. Note we're shifting the actual function we want to transform by the same value we're shifting the step. This is equal to e to the negative as times the Laplace transform. So basically, if I have a step function that's going to take the Laplace transform of whatever the function is, find the table of your choice and pick out what you're looking for there, and then you're just going to multiply that by an e to the negative as. We can show that this is true by using the definition of Laplace transform again. F of t minus a, u of t minus a, dt. Well, again, that's really only defined on the value from a to infinity. So we're looking at the shifted function. We make a substitution that v is equal to t minus a. So we get e to the s v minus, or times e to the negative sa f of v dv. In terms of v, the sa is just a constant. We can pull that out of our integral, and then now that we have essentially a Laplace transform of the function f. It's using a dummy variable v instead of the t we set out to do. But essentially what that shift did was say, hey, this is just your Laplace transform already shifted, thanks to that exponential there. So we pull that constant out. We get e to the negative sv fv dv. But hey, that's just the Laplace transform of f. So we have set out, or we have proved what we set out to prove. If we have, again, so kind of in reverse order, we want to do the inverse Laplace transform, L to the negative 1, of e to the negative as times big F of s. That is going to be equal to the shifted function f of t minus a, u of t minus a. So these are things to look for when either you are doing a Laplace transform. What do I turn my right-hand side of the equation into with those windows and those steps? Once I've done that, I probably need to get some steps back into that. They were there to begin with. They should probably be there in some form after the fact. So if I have an exponential times a known expression of an inverse Laplace transform, Laplace transform, my final thing is going to be that function shifted by a times the appropriate step function. For example, if I want to find the Laplace transform of t squared times u t minus 1, so our step is going to start at 1, and our function is going to be quadratic. We use our identity over here we need to use our identity where we have f of t minus a times u of t minus a. Here, a is equal to 1. This t here isn't shifted as is. So we need to think a little bit. And we need to think what function that when we subtract 1 from it gets us t squared. And so what we end up with is we're really looking at the Laplace transform of t plus 1 squared. If I subtract 1 from t, if I replace t with t minus 1, I get the t squared that we started with. So we do need to kind of shift our function to make sure it matches what the step function is doing. A way I kind of like to think about that is like add the opposite of what you're subtracting from the step function. Here we added 1 so that when we shift things properly, putting in t minus 1 cancels out the 1 that's already there and gets us just t squared at the end of the day. Our identity also says not only do we shift the function back, but we have to multiply by e to the negative as. Here a is just positive 1, so we get an e to the minus s out front. We can expand this and then use a table to figure out what the resulting total Laplace transform is. So we get e to the minus s times the Laplace transform of t squared plus 2t plus 1. And then we apply linearity to just get the result. So e to the negative s is going to multiply. T squared becomes 2 over s cubed. That's this kind of like t to the n gives you n factorial over s to the n plus 1. Same thing here. We get 2 times s squared, and then the 1 just gives us 1 over s. And that is the Laplace transform. Another example we might see, working with trig functions, for example. We want to look at cosine of t from u. to t minus pi. Well, again, we're going to get an e to the negative pi s out front. We get an e to the negative pi s out front from the step function, and then we're going to evaluate the Laplace transform of cosine of. To shift it properly, we're going to do t plus pi. Which really is just cosine again or negative cosine by normal trig identity stuff. So we look at our table, we find where cosine is, and we get negative e to the negative pi s times s over s squared plus 1. So we look at what our step function is shifting to, we modify our function to match that shift, apply any known Laplace transforms or trig identities to simplify it, and then use your table to get the final result. So now, last to finish off this topic here, we're going to do a little example borrowed from physics. We're going to look at the current in an LC circuit. So an LC circuit is one that consists of inductors and capacitors together. So L is an inductor, C is a capacitor. And we're going to set up a second order differential equation looking at the current in that circuit as a function of time. So we'll have I double prime plus 4I t equals g t. We have the initial conditions that I of 0 is 0 and I prime of 0 is also equal to 0. This g of t is going to be set up so that it's equal to 1 at the beginning, from 0 to 1. Then suddenly we're going to flip it back the other direction. And then after that, we'll stop. 2 seconds was enough, and so we'll go to 0 after that. Our goal is going to be to apply the Laplace transform to the left-hand side using the normal relationships between the derivatives there. We're also going to do it to the right-hand side. And now that our right-hand side is piecewise, we need to employ window and step functions to get that in the correct form. So if we do the left-hand side, we're going to get s squared times I of s minus si of 0 minus s prime of 0. So this here is just the definition of the second derivative as a Laplace transform. Because our initial conditions are both 0, this is kind of nice. These two terms drop out, so we're just left with s squared times our transformed version of the current. I guess we should give that a different name. So we'll call that J instead of I. And then the Laplace transform of just I by itself is J. That's what we called it now. So the left-hand side is going to become s squared J of s plus 4J of s equals the Laplace transform of G. So we need to figure out what this G looks like. So we're going to rewrite G as some windows here. And it's really going to be a window function from 0 to 1. It's just equal to 1 in that range. It's going to be negative 1. So we're going to subtract a window function from 1 to 2. And that's kind of it. It's 0 beyond that. And so if we want to write this in terms of the u's, we're going to get u of t, that's our 0, minus u of t minus 1. So that's the other bound of the first window function. And then we're going to subtract from that u of t minus 1. That's our first one, minus u of t minus 2. So what we end up with is u of t minus 2u t minus 1 plus u of t minus 2. So these two t minus 1 functions combine, they're both negative, and then the minus sign distributes to the one on here for the t minus 2 term, and we end up with that. We can use the fact that the u of t is just really equal to 1, so that will kind of help us simplify things a little bit. So at the end of the day, g is 1 minus 2u of t minus 1 plus u of t minus 2. So if we carefully apply the Laplace transform of that, we get g of s, big G, is equal to 1 over s minus 2 over s e to the negative s plus e to the negative 2s over s. So really, the functions here are just 1 over s, but because of the window function here, we pull out an e to the negative s, negative 2s here because we've shifted by 2. So we always have an e to the negative as attached to our step function. So we've got the right-hand side. We've got the left-hand side. Our goal now is to put the 2 and 2 together and then work out what j ends up being. So we have s squared j sub s. Get these wires out of the picture here. Plus 4j of s equals 1 over s minus 2 over s e to the minus s plus e to the negative 2s over s. Cool. We can factor out the j and divide by s squared plus 4. So j sub s is going to be equal to, these are all in terms of, well, I'll do it like this first. We're going to get 1 over s times s squared plus 4 minus 2e to the negative s over s times s squared plus 4. They all have the same denominator, in other words. And then the last term. And so what we ultimately have here is some function, 1 over s times s squared plus 4, with a bunch of constants and exponentials multiplied by that. So we can think what we really have is some inverse Laplace transform function minus 2 times e to the negative s of that same function plus e to the negative 2s times that same function. If we can figure out what this f sub s is, we can then find the inverse Laplace transform and then just kind of plug in the ultimate result there. So we'll have to use partial fractions to figure out what this thing looks like. We know that we have a constant term and a irreducible quadratic term. So we'll get a over s plus b s plus c over s squared plus 4. So that's using the normal partial fractions decomposition. We'll cross multiply to kind of figure out what the numerator needs to look like. So we'll get as squared plus 4a plus bs squared plus cs equals 1. Our original numerator was 1. We need the numerator over here to equal 1 as well. And now we're going to combine like terms. So we have quadratic terms in S, we have a linear term in S, and then we have a constant term in S. Really, we only want the constant term left. So we have 4a equals 1. So a has to equal 1/4. Knowing that, we can go to our quadratic term over here. And we can say, well, a plus b needs to equal 0. There are no quadratic terms in the original numerator. And so now that we know that a equals 1/4, we know that b equals negative 1/4. And then there's no linear terms at all, so C is just 0. So that one wasn't too bad. And what this means now is that we can take this function we want to find the inverse Laplace transform of. We've decoupled it into partial fractions, which are a little bit more digestible, in which we can find things that match in a table. So we have 1/4 times 1 over s plus 1/4 s over s squared plus 4. And this was a negative 1/4, actually. 1 over s is just the inverse Laplace transform of t. S over s squared plus 4 is an inverse Laplace transform of a cosine function. We have a 4 is 2 squared, so it'll be a cosine 2t. So looking at this, we get that little f of t should be equal to 1/4 minus 1/4 cosine of 2t. Now, this function is what this one turns into when we apply the inverse Laplace transform. So we're going to use our identities with an inverse Laplace transform and a exponential to write this as a sum of kind of something that looks like this, and the later ones in the sum here will be multiplied by a step function. So we apply it term by term. The current as a function of time is equal to 1/4 minus 1/4 cosine 2t. That's the first term by itself. We inverse Laplace transform that guy, and we get this. That's going to be minus, I'll write some parentheses here, 2. We're going to have to shift our function by 1. That's our exponential. And then that will also be the resulting step function that goes along with that. So the 2 is going to turn those 1/4 into 1/2. Cosine of 2t minus 1. And then that whole thing is multiplied by u times t minus 1. And then we'll do it one more time. We have a e to the negative 2s, so we're going to shift our cosine by 2 and multiply by that step function. So plus 1/4 minus 1/4 cosine 2 times t minus 2 times u times t minus 2. And there you have it, a big, long, ugly function. But we only had to do the differential equation solving process once. We didn't have to do it 3 times for each of the subintervals there. And so this is efficient. Yes, there's some partial fractions work in there, but there are tables in your textbooks and online. You can look at those. They tell you how to do that once you get things in the right form. The rest is just pattern matching. Once I have, this same function here multiplied by different exponentials, I recognize those as a step function. It's going to make me have to shift my function by the argument of that exponential, the constant in front of the s, 1 here, 2 for the second one. But we're really just matching that pattern. If there's an exponential tacked on, that just means there's going to be a step function tacked on with the appropriate shift. So there you go. That is discontinuous functions with the Laplace transform. Hopefully you found it useful, and enjoy.